So hello everyone. So it's a pleasure to welcome Alexandre Marcowith for today's colloquium. And Alexandre has been a long-term member of the Laboratoire Univers and Particules in Montpellier, the LUPM, and also of the HES and CTA collaboration. But Alexandre is mostly a theorist, so he's an expert actually in the physics and in the astrophysics of cosmic rays. And recently actually has been interested in the possible impact of these relativistic particles on the dynamics of the interstellar gas and the feedback of galaxy formation in collaboration with our host, Johan. But today he will be speaking mostly on a subject that he has been working on recently and that he has developed with collaborators, which is the role of energetic particles in young and active stellar objects. So please, Alexandre.
Thank you very much, Martin and Johan, for your invitation, your kind invitation, and it's a pleasure for me to, discuss this, let's say, new topics and maybe emerging topics. And so I hope you can hear me well and you can see my everything well. So on the role of energetic particles and cosmic rays in young and active stellar objects. So this is the work I've done in collaboration in these recent years with these people, also mostly with Marco Padovani at Archetri Observatory, but also, for instance, Christophe Sotti. Okay, so I cannot move on with my slide. Ah, yes. So so let's say the outline of this talk is the following. So I will start to discuss with the scientific interest about why it is interesting to consider energetic particles in such environments. Then I will go through observations which probes the presence of a non-thermal component in jets and disk of these objects, especially to what regards ionization rates and synchrotron radiation in jets. Then I will move to theory to let's discuss a bit what I have done with my collaborator recently, especially on jets, to explain ionization rates and synchrotron radiation. But then I will also go through, let's say, a bit more speculative aspect of energetic particle in these environments as of the star and disk interface, magnetic interaction especially, and which can be of interest of I explained somehow the ionization of the accretion disk and the launching of jets, and then go to the conclusion. So young active stars are you can find some reviews about these, and energetic particle in this object have been discussed, for instance, in this review by Feigelson and Thierry Momerle. And also a nice introduction also has been proposed by Manel Gödel during a summer school. So a schematic view of this object is as follows. So inside the object you have a magnetized star, which is in fact rotating, and which has a magnetic field which is in interaction with a magnetic field which is carried by an accretion disk. And from this, either the disk or the star itself, you have a launching of jets up to rather large distances into the interstellar medium, up, let's say, to a fraction of parsec or 1 parsec. And so they are probed by some outflows with an external outflows in molecular materials of few kilometers per second, and in the inner part a fast outflow of several 100 kilometers per second. more specifically, I will discuss young stellar objects of mass between, let's say, 0.2 to 2 solar masses, which are known as T2 stars. So these are the precursor of our sun, in fact. And this is why they are very important and interesting to study. So the sketch of the time evolution of this object is roughly as follows. So from the infalling molecular gas and core, you start to form a protostar, which is quite enshrouded inside this envelope first. This is the class 0 T2, which a very young age, and which shows mostly the radiation from the stars. So you have no evidences of disk radiation yet. And then after some time, the envelope is dissipated, and then start to appear an emission from an accretion disk, and also appearing some outflows. So this is a so-called class 1 object with a thick disk. Then around, let's say, 1 million years to 10 million years, you have the so-called, let's say, pre-main sequence objects, which are the class 2 and class 3, so which are divided in classical T2 stars, where you still have a thick, optically thick accretion disk and strong outflows, and then weak T2 stars, where the disk is less, emission from the disk is less prominent, and it's even optically thin and even non-existent. And finally, you will get to the main sequence object with the formation of dissipation of the circumstellar disk and to the production of planets. So, as I told you, these objects produce strong jets and bipolar outflows, so with a double structure. So externally you have a molecular gas moving at a few kilometers per second, and then inside you have collimated, possibly by the magnetic field, fast jets, and so which are producing some substructure inside the jet. So as you may see here, you have a kind of knots along the jets, and at the termination shock of the jet, where the jet is interacting with interstellar medium, you have some hotspots. And so the size of the jets are about 1000 AU to few parsec, as I told you. The speed can be rather important, but for between 100 to 300 kilometers per second for, let's say, low mass, so T2 objects. And for higher mass young stellar objects, you can even reach 1000 kilometers per second in some cases. The typical temperature is about 10 to the 4, 10 to the 5. So something which is important, especially to what regards particle acceleration, is the degree of ionization along the jet. So this is an information which is rather difficult to get, and especially also this ionization fraction is varying along the jet, and it's basically between 0.01 to 1. So you still have a substantial fraction of ions, let's say. And the magnetic field strength is also difficult to derive. Usually it can be derived, for instance, using some equipartition argument with the synchrotron radiation. And so you have typically milli-Gauss strengths for the field. So I would just like to mention here also not only T2 stars, but also another category of stars, which are the M-dwarf stars, which are interesting because they show strong magnetic activity. So these are lower mass, so they occupy the lower end of the Hirschsprung-Russell diagram here. So these are cool objects with lower luminosity. But through the Zeeman Doppler imaging effect, people are able to reconstruct the stellar magnetic field, which can go up to 1 kilogauss. And so this magnetic activity of M dwarfs is important to what respect of planets, because these objects are interesting to study planets, because they are, like, let's say, a kind of scale down of our solar system. And so the planets are much closer to the stars, and then much more strongly under the effect of this magnetic activity of the star itself. And so you can you know, some well-known objects have been discussed in the information, for instance, TRAPPIST-1 and Gliese 866. So this magnetic activity has some deep impact over the atmosphere of these planets, especially if they are in the so-called habitable zone. So why investigating energetic particles in these objects? So there are different ways to justify it. So these particles are interesting for different aspects, because so they can produce some ionization, so they can penetrate where let's say photons, high energy photons cannot penetrate, especially UV photons. X-ray photon, it's a bit more different, but even at very high Coulomb density, only energetic particle can penetrate, let's say above 10 to the 24, 25 per centimeter square. So a side effect of ionization is production of heat, and so injection of heat in some part of the system is interesting, especially if you want to launch jets, for instance, using magnetic centrifugal effects. It's easier to heat a bit the matter to help it to follow the magnetic field line and get untrained with the jet. Of course, they are also interesting because they are a strong source of spallation, and especially production of light and radioactive elements we have we can also measure actually in our solar system through the meteorites. Energetic particles can be traced using either synchrotron radiation, so with which they produce non-thermal and polarized emission at radio and possibly X-rays. I will come back on that. They induce particular chemistry with producing ions such like HCO+, N2H+, and possibly they can be probed through higher energetic emission, such like gamma rays. So there are prospects to investigate gamma ray production in this object, especially with the advent of the Cherenkov telescope array. So just a word of caution here. By energetic particle, I will mean two types of populations. So either the particles which are in situ accelerated, so such like stellar energetic particles, for instance, accelerated as stellar flares, or cosmic rays. So cosmic rays that is external population of non-thermal particles which are produced, for instance, by supernova remnants. And in this seminar, I will advocate in favor on the role of in situ accelerated energetic particles. But of course, both populations have to be investigated, considered to investigate the role of this energetic particle in these environments. Let's move now to observation. So on the non-thermal processes in these objects. So there have been a review recently published in the Space Science Reviews. So I can, let's say, first start with so ionization rates anomalies which have been detected thanks to the Herschel observation of two particular objects. They are quite different objects. The first one is OMC2 FIR4. In fact, it's not an isolated star. It's a protocluster of stars. which is composed of so T3 type stars, but also with stars which higher masses. And so what has been done here is through Herschel is to derive from the lines associated with HCO plus and N2H plus the abundances of these elements. And if you calculate the ratio of these abundances under some framework, you can reconstruct the cosmic ray ionization rate. And what is found is that in envelopes surrounding the star, either the warm envelope rather close to the star, let's say at a few thousand AU, ionization rates of, let's say, 5 order of magnitude above the standard Spectral value, which is about 310 to the minus 17 ionization per second for molecular hydrogen, has been found. So there is a strong source of ionization here. And also for the outer envelope, let's say the cold envelope, still 3 order of magnitude above have been found. And these are consistent with the meteoritic measurements done in our solar system, which points toward a strong source of ionization particles in the early solar system. There is another source of interest. Here is bow shock, so the end of the jet of T3 objects. It is L1157, which shows, again, using Herschel observation and this ratio of these two species, you can reconstruct using a different model. Now you have to go through a code which compute the abundances of this element behind a shock. But then if you compare it with the observation, they are consistent with ionization rate of about 310 to the minus 16, so 1 order of magnitude above the standard Spectral values. Another hint of, let's say, strong activity in these objects is, of course, through thermal X-rays. So this is not yet non-thermal, but at least they are a good probe of the magnetic activity in these objects and magnetic reconnection. And so these objects are well known to produce strong flares at X-rays with luminosity between 10 to the 31 to 33 erg per second, and which is likely associated with a magnetic power which is released during reconnection events, strong reconnection events. And with a flare which duration is about a few hours to, let's say, a fraction of day. The flares are also more frequent than in solar flare and are more luminous. So these energetic events are much more stronger in this environment than in our actual sun. The X-ray activity is, can be associated with a stellar disk or disk magnetic field. So as you may see here is an example of idealized view of, so you have the accretion disk, the star itself with some magnetic loops, which producing the flare, which is observed here through the, especially the thanks to the Chandra satellite. So you have a typical flare with this fast rays and slow decay. And from this time profile, you can reconstruct the flare loop size with respect to the stellar radius. And this has been done with quite interesting work done by Favata and then by Getman, which has investigated the sample of flare in this Orion Nebula T3 objects. This is so-called the COPE survey by Chandra. And what they found is that, in fact, the size of the magnetic loop associated with the flare are can be much larger, in fact, than the stellar radius. So that means that likely these flares are associated with in fact, the magnetic field interaction of the star with the magnetic field of the disk. it is the largest loops appear for the high accretion objects, so where you have a strong accretion disk. Then another probe of energetic particle from flares is also through radio data. And this has been for long. This is a nice review by Andre in '96 here, which shows some radio emission variability in the hour time scale, let's say few hour time scale, and which shows to non-thermal emission, which also is polarized and shows some circular polarization. So here you have two examples of two different objects, which are likely, in fact, binary objects. So you have two T2-like objects orbiting together, and then a circum-binary disk. And so these flares are interesting because they are non-thermal. So this is a direct probe of non-thermal particle acceleration, electrons acceleration in these objects. The mechanism at the origin of this flare can be either incoherent synchrotron radiation or coherent, let's say, Maser synchrotron process, because you can have a high brightness temperature and high degree of circular polarization. And these are interesting, especially for the next generation of radio telescope like SKA. In jets, so there are also some evidences of non-thermal radiation, like here is an example, quite a remarkable example of the object HH8081. So here I present you some radio data from the JVLA at around a few gigahertz. And this is a zoom on a jet. So you have a strong radiation, and you see that the intensity is varying along the jet, and also as well as the spectral index. So the spectral index is varying from negative to positive value along the jet. Positive index is related to region where the jet is narrowing, and negative index is associated with the region where the jet is widening, and negative index is a signature of synchrotron radiation by mildly or relativistic electrons. And so it may be associated with the formation of shocks through reconnexion shocks along the jet, and behind the shocks you have energetic electrons which are radiating this synchrotron radiation. This is not an exception. You have several young stellar object jets which shows non-thermal radiation, and this is maybe a non-exhaustive list. I think from the more massive to the less massive cases. There have been a recent survey of 1,000 sources by Purser and collaborators. So this is in fact a PhD thesis, and it's quite interesting also for the next for SKA, so the next radio facility which can observe these objects. There have been some claim of hard non-thermal X-rays above 2 keV in this object HH8081, but I'm not sure that it has been confirmed yet. Okay, so we have finished with the observational part. So let's move now on the acceleration, and so how can we produce and explain the production of energetic particles in these objects. So we have developed a series of models, mostly with Marco and also with Annabella Rodo recently. So the basic idea is not very complicated. It's the following. So here is a sketch of, let's say, a T3 star. Of course, it's a theoresis sketch, very simplified. Here you have the star, so the accretion column. So you have a material from the accretion disk, which is channeled through the magnetic field to the start, and then you have production of accretion shocks there. Then you can, as I told you, have shocks along the jet through either recollimation or non-steady ejection. And then you have the termination shock, so the interaction of the jet with the interstellar medium, which can produce a strong shock here, usually a weaker bow shock, external bow shock. And so our work was first to derive the, let's say, the parameter necessary to calculate the particle acceleration efficiency in this object, especially the shock speed, the temperature of the medium, the density of the medium, the ionization fraction, which is important because neutrals can damp magnetic fluctuation, which allow the particle to be scattered back and forth the shock and get accelerated, and the magnetic field intensity. So this parameter is usually not really easy to derive from observation, and so sometimes we have to rely on numerical simulations for that. And so we consider three types of shocks. So a shock in the accretion envelope, which in fact have been shown to be not fast enough to accelerate particles, but then you have faster shocks here at the accretion columns and along the jets, which are much faster and allow particle acceleration. So these are the typical spectral energy distribution of the particle we can get. So here is a thermal component, and then you produce a non-thermal component of either protons or electrons. Here you have different type of model. It's for the jet model, depending of the shock speed. So this is a weak and the strong case. And here is a model of accretion shock along the accretion column. And then you see that the maximum energy, especially for protons, is around, let's say, 10 GeV. So these are not, let's say, cosmic ray, likely cosmic ray sources, but the particles are energetic enough, especially to populate this range of a few MeV to allow some ionization. So with this particular model, we have tried to explain this observation of ionization fraction in this object. So here are for the IMC2 FIR4 case, we consider mostly the particles which are produced at the accretion columns, so on the start, and then which propagate toward the envelope, either through diffusively, so let's say a random process, so with some diffusion, or ballistically, so diluted as R-2 with respect to the distance to the star. And so you see that they can encompass the level of ionization degree which has been observed by air shell. Of course, this is rather crude because we do not account for any magnetic field structure. As these particles are charged particles, they are sensitive to the magnetic field structure. Then this is the case of L1157. You have to look at the green curve here. This is the two component effect of ionization. Here you have if you rely ionization only of external cosmic rays, so we use the standard cosmic ray spectrum we have around Earth thanks to Voyager data. And you see that at the distance where you have the hotspot, the ionization produced by this external cosmic ray is not high enough to explain the 3 to -16. So you have to really rely on the in-situ accelerated particles. This is why I think in-situ particle acceleration along the jets are important to explain this data. So since we have continued and to work on this interesting protostellar cluster, which is a quite complex, in fact, object, because since we first published our model, there have been some VLA observation on this object, and in fact, it is composed of two different star production sites, and you have another one, HOPS 370, from which has been observed a jet where which so the emission has been observed by a VLA and at three different nodes along the jet. And in fact, interestingly, these nodes are within the contour of the ionization rates detected by Herschel. So our idea was to try to explain, in fact, both features, that is the ionization rate deduced by Herschel and the non-thermal emission along the jet, using one model, and so particle getting accelerated along the jet. So this is a kind of different interpretation of what I showed you previously from the propagation from the accretion column. And so we were able to, in fact, to reproduce both. So we use, in fact, the ionization fraction to fix, in fact, the particle normalization. So at low energy particles are fixing this ionization fraction. So this is the solution you see in the parameter space of the shock speed. You have some uncertainties about the shock speed, the exact shock speed, and the fraction of the kinetic energy of the jet imparted into the particles. So this is rather small, you see. So you have a teeny range of in the parameter space, which allow you to explain this ionization rate. And then once we have fixed the normalization, we have tried to adjust the radio data. So we are happy. So we were successful in doing this. Another application is a digital shock. So there have been some observation by the VLA and GMRT of the hotspot of this object, and so we were able to fit this with our model of termination shock of the jet. And since our publications have been also further observation by LOFAR, so which shows, in fact, a softening of the spectrum likely produced by synchrotron self-absorption. So I just add here the two data points of LOFAR, and so our model, which is in black here, so we can rather fit well the high energy radio data, but then we have still to account for the synchrotron self-absorption. We were not able to do this at the time of the GMRT and VLA data. Then we consider also that for higher mass objects, you have faster shocks, so up to 1,000 kilometers per second. And then as the acceleration time scale is scaling as the square of the shock to the -2, then the acceleration time scale can be reduced, and then you can get higher energies. And so we start a prospect of gamma ray emitters in massive young stellar objects. This is done work done with Annabella Arodo and Marco Padovani. And so here is a case of three sources. So we adjust the synchrotron data, radio data, to fix the magnetic field. And from magnetic field value, we are able to calculate the acceleration particle efficiency and the maximum energies, which are not terrific, I should say. It's from proton, especially, you have about, let's say, 200 GeV. But in fact, you have some uncertainty about this exact value, because for instance, the density, the exact density is not well known, the exact shock speed is not well known. So it may vary, and it may still be of interest for the CTA observatory, which is should be operational within a few years. And so there is a dedicated work to evaluate how much of this object CTA could detect. So I finish with the jets, and let me come back to a bit more prospective aspect of energetic particles in these environments, which is a zone of interaction between the star and the accretion disk. So here, in fact, there is a growing research activity on this aspect, and I think a list more or less exhaustive list of published work. So you see that there's a kind of acceleration of from 2015. And also there are some work which is done, especially at the working group at Bern in the EC Institute, on also the impact of the energetic particle for more evolved objects, let's say like our sun, and the impact over the exoplanet habitability, especially the impact of the energetic particle of the atmosphere of this planet. If you have a strong flux of particles from the star, for instance, how can it modify the ozone abundance? So as ozone will be an important marker of possibility of the appearance of life on some planets. So coming back to the let's say tertiary objects. So here is a sketch of the accretion disk and the star itself with the magnetic field in green. And so you see you have multiple zones where you can accelerate particles through first magnetic reconnexion. Of course, you associated with flares from the stars, but also with magnetic reconnexion of interaction of the magnetic field from the star and the accretion disk at the truncation radius of the accretion disk, or within the wind and the jet. Here you can have also interaction of in a magnetic field. Also, if your accretion disk has a bit of level of turbulence and the magnetic field is somehow tangled, you can have some reconnexion around the accretion disk. So let's say more possibly in the inner part of the disk, so in the, let's say, up to 100 AU. You can accelerate particles through magnetic turbulence, so the stochastic Fermi acceleration, let's say, and also in shocks. As I told you here, I discussed already these accretion shocks and the shock in jets, but also you can have acceleration of particles through coronal mass ejection associated with flaring activity of the star. So what people have tried to do from now is the following. So they have basically made somehow a crude modeling of energetic flux expected from this object by upscaling what is observed from our sun. So our sun, we know, let's say, the fluence of energetic particle produced by our sun, and we know the X-ray luminosity. So they just use a simple rules and to evaluate the flux, the luminosity imparted in this energetic particle from this object. And so this is higher because the X-ray flux in this object is higher than in our sun. So they can reach luminosity up to 10 to the 28 ergs per second. And then from that, they they allow the particle to propagate from the star toward the disk using some prescribed diffusion coefficient. Here it's diffusion coefficient about 30 times the so-called Bohm values. That is the mean free path of the particle at the Bohm value is equal to their Larmor radius. And so once they have the flux of the particle which are hitting the disk, calculating the ionization loss, they are able to reconstruct the ionization rate inside the disk produced by the particle. This is the ionization rate of molecular hydrogen. And so this can be quite important, especially in the zone of the disk nearby to the star. Here is also how this ionization rate evolves with the different prescription of the diffusion coefficient. Of course, as you decrease the diffusion coefficient, you will maintain more the particle towards the stars, but you will increase the ionization rate in that inner part up to 1 AU. So this is an interesting work, but of course it suffers from this is a prescription of the, let's say, the diffusion. And then, of course, it would be much more satisfying if we can construct a model of based on more realistic structure of the magnetic field and this environment. Also, this is a difficult work to do because you have multiple sources of ionization of the accretion disk in this object. So you have stellar energetic particle, external cosmic rays, and X and UV rays, and also radioactive elements which are produced in. And so which one is dominating is in fact not so clear actually, and it's strongly dependent on what type of model you assume for either the X-ray luminosity, the stellar particle, or the external cosmic rays. And so you see that the solution you can get, this is a work done by Christian Rabb and collaborator using a chemistry code. So, and the source of ionization does vary strongly depending on the model you have, from being dominated by a stellar particle or by X-rays to the upper level of the magnetic of the accretion disk. And so you can have a contribution for external cosmic rays more deeply inside the disk. So let's say another way to investigate this effect of energetic particle over the disk structure is also that to consider the time-dependent effect. What I've presented you previously is time-independent. And the problem is that most of the chemistry models are not time-dependent and do not include also magnetic effects. So what could be of interest is also to evaluate the impact of this flare and energetic particle over the dynamical evolution of the accretion and ejection. And this is an example of some work done by Salvatore Orlando using a 3D magnetohydrodynamic simulation. So here you have the early evolution of the disk through a flare episode up above the disk, close to the star. So here you have the disk, the stars, the magnetic field of the stars, and the poloidal velocity field. And you see that the flare can strongly disrupt the disk. Here is the density and temperature evolution, and in fact, lately it can also trigger some accretion onto the star, and possibly some more ejection. So you see, you have really two sides of let's say the effect of flare over the dynamical processes which are ongoing in these objects. So this is why we decided in Montpellier to give an opportunity to a young student to start his thesis with Christophe Sautier. And so the idea of this work is basically to start from a disk solution produced by this Prodimo chemistry code. And here you have the density profile in the disk, and then to consider you have a flare based on the Chandra data, and let particle propagate inside the disk with an assumption of the magnetic field configuration. Here, for instance, if you have a vertical magnetic field, but we can add other type of magnetic field. So of course it's important to have the magnetic field to have a guide for the energetic particle. And here is an evolution of the particle distribution as the particles are moving toward the disk. And you see that the ionization losses are carving the low energy part of the spectrum because so the particles are losing their energy. And so particles are depositing some heat and ionizing the disk. And so the idea now is to go to a more realistic model, which includes some time dependence. So, and for that, we will sample the flare properties over the COOP, so it's Chandra data. So we will sample the jet luminosity, temperature, etc. And also we'll vary the position of the flare from the star or at the interface between the disk and the star or farther away in the disk, and to reconstruct a time-dependent ionization level of the disk, which is important, so including recombination between two flares, the matter will recombine. So, which is interesting because then if you to evaluate, for instance, the impact of these energetic cosmic rays and X-rays over, for instance, the triggering of the magnetorotational instability, which require a minimum level of ionization. So let me finish this talk by, let's say, I think a bit more prospective words. So I think we have great opportunities soon to investigate this aspect more deeply, thanks to the new facilities which are now at the horizon of a few years. So of course, as I told you, there is a SKA. We already have some very nice observation of ALMA, especially which can probe the disk properties and the level of turbulence. But it is more, let's say, for the external disk, let's say for distances larger than 100 AU from the star, or a few tens. So you will have the GWST telescope, which should be launched soon, and it is a very interesting because it can probe through near infrared the inner part of the disk, and especially it could be of great interest to probe the level of turbulence you can have inside so for the disk close to the star. We have to keep an eye, of course, on the data which are coming from the Parker and Solar Orbiter probes, which are ongoing and which are now actively let's say studying the solar activity, because it's very interesting to have a better ideas on the physics of energetic events in the links with the solar activity, and then to scale it to these young stellar objects. I think there are some opportunity for high energy astrophysics still in the MEV domain, because it would be of interest to have some MEV instruments, not maybe to look for particular young stellar objects, but maybe for cluster of such objects. So I'm thinking, for instance, to this OMC2 FIR4 object or FIR3 to try to catch some diffuse emission associated with light element production. And as I told you, it can be of interest for also CTA. And finally, I think it's also for objects of interest and particle acceleration in this configuration are of interest for laser plasma experiments. So there have been already some work on these particular setups linked with this object. So that's basically my conclusion. So I have advocated in favor of energetic particle acceleration in this object. I've tried to show you that why they are interesting. So not, and they may be probed by a different instrument or facilities which like SKA and CTA. They are interesting because mostly they contribute to enhance ionization rates in these objects, and these are for many aspects of strong interest for the dynamical evolution of these objects. And there are more, of course, a bit of speculation of this inner part, but so we are working hardly on this subject to see if it's relevant or not. I'm not saying that the energetic particles are very important for the dynamic of this object, at least in this central part, but I think it's worthwhile investigating. So thank you for your attention.
Thank you, Alexandre, and for this presentation. And now we'll take questions, if any. Please raise your hand or open your microphone.
Yes, Alexandre, this is Martin.
Yes, yes.
I have a question. So I think in the main part of the text of your presentation, you discussed acceleration in shocks propagating along the jet.
Yes.
And you showed that you could reproduce the radio data. But so do you have a preference for the acceleration mechanism, whether it would be those shocks or whether it would be acceleration in flares or in turbulence along the shock? Because I mean, I guess that there is one hidden assumption that is the slope of the accelerated population will control the slope of the radio data, for instance. And therefore, these different mechanisms could have a signature there.
Yes. Here is an example, I think. So maybe we can move to this part where it is here. So indeed, in fact, in the radio data which shows non-thermal signature, in fact, the spectrum is around 0.5, so which is a standard signature of the optically thin synchrotron radiation produced by a population of energetic particles with energy distribution of E-2, which is let's say the standard solution you got for shock acceleration. And so this fit rather well, but you see that you have other cases where it's rather different. So as you have shocks, you have turbulence and tangle magnetic field, I think we cannot, of course, exclude other type of processes like reconnexion, and this is also something which is actively investigated, especially in relativistic jets and for compact objects. I mean, it's I mean, all the physics, and probably your question is related to this, is that these objects share a kind of similar physics to compact objects. Instead of having a star at the center, you have a black hole, and still you have accretion disk and strong jets and relativistic jets. And of course, the regimes are different because you have more relativistic regimes or different magnetization. But I think still, of course, we have the possibility to include a reconnexion. And I think, and so this is why it motivates our work with this thesis, is that reconnexion is an unavoidable process to consider associated with the flaring activity, X-ray flaring activity of this object. As you cannot rely on shocks. I think you have to consider reconnexion and dissipation of the magnetic field in these events. I don't know if I have properly answered your question. I've tried.
Yes, thank you.
Thierry, yes.
Hello. Hello, Alexandre. Good to
Hello,
see
Thierry.
you,
Yes.
even in 2Ds instead of 3D. I have a sort of broad questions about the energetics, the overall energetics, because in these type of problems, you have a number of, first, normalization to some parameters, observational parameter, for instance, the X-ray luminosity or whatever. And you have also parameterization of the, for instance, the acceleration efficiency and other such factors. So in the end, what you try to fit is a particle spectrum with a given spectral index. You get the maximum energy. You get a number of parameters that are intrinsic to the mechanism. But what about the energy input compared to observations? Observations give you basically luminosities, energetics, luminosities. And how do these luminosities match actually? And what is the main uncertainty on the main factor that could give you a handle on the absolute luminosity, let's call it luminosity in general, the energy output per unit time, especially if you're dealing with time-dependent phenomena. How does this fit together?
So difficult question. So the idea is, well, when you accelerate non-thermal particle, you extract energy from, let's say, some another source of energy. And so for jets, it's a kinetic energy. So, and then you have to make some assumption about, as all diffusive shock acceleration problems, is what type of fraction you should expect from to be imparted into the non-thermal particle into this. Yes, from the kinetic energy. Here is an example. So you can see that. So of course it's in normalized quantities, not very easy to read. But so basically, it's let's say you have a very small fraction of the kinetic energy here, which is recede to the non-thermal electron population, about 10⁻⁵ in pressure. So the kinetic pressure, so rho v shock square, which is so very small. So this a good aspect is that we are working in the test particle case. So we have no back reaction of a non-thermal particle over the shocks. This is a good aspect because for supernova remnant, it's not the same story. But so you see, you need really not much. So we are, let's say, energetic constraint, at least in this case, are not very constraining for us. It's you don't need much to extract from the kinetic energy of the shock, let's say, shock material, to explain this data. This may a bit the story may be a bit different in this environment of close to the disk and the star. So here I have yes, I have not the number in mind to fully reply to you, because yes, it's rely also on the mechanism of particle acceleration in reconnexion, magnetic reconnexion, and this field is I think quite still open, because if we know more or less how particles are accelerated at let's say through diffusive shock acceleration, in magnetic reconnexion it's much more open. I think I've listed about 7 ways you can accelerate non-thermal particle in reconnexion events. So you don't only have the electric field in the reconnexion layer, which can accelerate particle, but in the nonlinear phase you have plasmoids, and so you can trap particles, etc. So this aspect is not obvious, and what we are doing now is very crude. I mean, we just take we just select some normalization of the non-thermal component to the, we are branching to the thermal component in reconnexion event, and then we are scaling our estimation on the sun. So basically this is what we are doing for this type of studies. So I think it's difficult to do another other way that relying on the solar data. Again, I don't know if I reply correctly to your question.
No, it's always a difficult problem. If I may, I would have another. It's more a comment than anything else. It's about the chemistry and the time scales. In general, the time scale for chemistry, and you showed one figure, are more in for chemical reactions about ionization in a dense medium, are more in the range of years, 1,000 years or more. So they would really, the impact of even variable acceleration on energetic particles would sort of average out in the surrounding medium. So in this case, the question that is implied is whether the timescales of the events that you observe in flares give rise to sort of cumulative phenomena that is at one predefined moment times zero, the phenomena which is unrealistic, of course, but let's assume that you start the mechanism and then you have these repetitive events. And then what perhaps you could address in the future, not now, but in the future, is that by assuming some kind of simplification in which you start the triggering and the time variable events, whether they sort of saturate after some time in terms of average. Well, either they will grow forever, for instance, or some mechanism like recombination or chemical reaction will saturate at a given level. And then perhaps you could think one day of trying to match the two. You have the source, which is time variable. You have the result of the impact, which is stable, which is sort of an asymptotic state. And whether you can match the two intensity, whether, for instance, you could check whether there is a characteristic time scale that you need to have enough particles to ionize to the observed level, or chemistry ratio, or whatever, or whether this, what I have in mind, my deeper, perhaps the question is whether, which are the relevant timescales of variability that will really give rise to some observable effects.
Yes.
You have some timescales, obviously, but are these crucial for the overall result that you observe in the interstellar medium, or would any other timescale do the same, perhaps quicker, but after 10,000 years you will have forgotten your initial conditions? That's the idea.
That is a very good question. So that is exactly what we plan to do. In fact, so this is it is a bit written here. In fact, this is our plan. Actually, because here is an example of one flare. So of course, this is not so interesting. And so we have selected one strong flare to have some effects. But of course, you have to sample first over the flare distribution, which has been derived thanks to the Chandra observation. So this is what actually we are doing. So for a given period of time, what we are doing, you are sampling using a kind of Monte Carlo method over some distribution. You are sampling your flare characteristic, and from your flare temperature and luminosity, you can scale the injection of X-rays first, and secondly of energetic particles. And so this is why also we are working with a guy from this Prodimo code, Christian Rab. This is a chemistry code, to evaluate for a given type of flare, what is the impact over the chemistry in the disk. And then, of course, we have to average the effect over some time scale. Here's the typical time scale you have at 0.1 AU is, let's say, 1/10 of a year. It's a Keplerian orbit. But also, maybe it's interesting also to compare with, let's say, time scale which are of interest for instruments. So because Chandra observed for a much shorter period. So I don't know how much we need to average our result in order to get a good comparison with observation. But this is something we have to think about, yes. Yes. And also I wanted to add that in between two flares, of course, we have to include a recombination, because this is matter we can recombine. And so in order to get an average ionization rate over a given period. That is more or less what you were saying. Yes, of course, it's an important aspect, yes.
Ok, merci Alexandre.
De rien.
Bonne chance pour le FR Codes, on sera là.
Oui, oui, merci.
Is there any more questions? Okay, I can ask one maybe. So the in terms, so you so the cosmic ray change the ionization state of the gas. So therefore, it changes the cooling rates and temperature properties, right? In principle. So do you expect from those mechanisms to change the structure of the first, second Larson cores and therefore of the action rate onto the star and the final star mass, right?
So at larger distances, you mean?
Yes.
Yes, that's a good question. Something I did not think about at all. So this is a kind of feedback process from young stars, let's say. And well, maybe, yes, it's. To be honest, I don't have the answer to this question yet. I just want to point out where it is. I'm lost in my slides. Yes, the data from Herschel, yes. Well, the difficulty with your question is that for now we have more or less only one object which shows such high ionization rate, and so why this object is particular is a bit puzzling. The point is that in this object you have also a precursor of more massive stars, so maybe it's connected. And then you see that we have only one object, but the level of ionization is huge. I mean, it's 5 orders of magnitude above the Spitzer value. This is a huge effect. And this is produced by energetic particles. It's difficult to explain this with radiation. So if it can be generalized to other objects, I'm not sure that there have been some positive detection of in other objects, but I'm not an observer. Maybe it could be worthwhile asking Cecilia, for instance, Ciccarelli. So potentially it can be yes, a good, strong feedback process. Yeah. And of course, this changes the situation for the, let's say, it could change the situation for the star formation rate. Yes. But beforehand, I think we have to have several observations of such a case.
Okay. Yes, Nathan?
Hello. Well, first, thank you very much for all of this. I have a question that maybe a bit simple, I'm sorry, but I was wondering if all those laws about disks and acceleration phenomena, do they scale well with other types of objects? So we've talked about Tittori stars. Would it work also for disks around compact object, for example?
Yes, that's indeed a good question. I was, yeah. So it's tempting here, of course, to replace the star by a black hole. And yes, actually, there is some common stuff of this if you do this, especially about ejection. So you have so large-scale jets which are produced either from the disk or from the compact objects by different mechanisms. You can have each time you have a Roger Blanford which is involved in so Blanford and Payne for centrifugal ejection. So I mean the magnetic field which is curved, and so the matter which is expelled. Or you can have some more electromagnetic process which is a so-called Blanford-Znajek. And there is a lot of research which is ongoing, in fact, actually, in this configuration using especially particle in cell simulation. So you have a group in Grenoble which is very active with Benoît Chirouti. And so but the point is in compact objects, the environment is a bit different. So you have the environment here is likely dominated by radiation. You have strong impact of radiation over the dynamics also. And this is something which is a bit different with this object. I mean, radiation, you can have a pair creation and so hot plasmas, and so this change a lot for the dynamics of the compact objects with respect to this. But we can find some similarities, at least in acceleration mechanism. I think it could be interesting to have to keep an eye. And if you are doing some, let's say, MHD simulation, you can try to adapt. And this is actually what we plan to do with Christophe Sauty, to adapt the code we are using either to one situation or to the other. So putting a compact object or a star in. So the answer is not, of course, yes or no. Is that yes, partially yes, but you have to examine the situation case by case. You have a relativistic plasma in one case. You have different magnetization, so the reconnexion regime is different, etc. So I don't know if I answer to your question. It's either.
Okay, if there's not any more questions, I think we can stop here.